They're a small one or do you have a big?
Yes, sir. Yeah.
All right, well, let's see.
Yeah, I do.
Okay, so let's please make a start to this afternoon session of the workshop. Our speaker today is Professor Haavard Rue, who is full professor here at KAUST in statistics. Haavard is very well known for his work in Bayesian computation, Markov random fields, and INLA over the last 30 years. Haavard has written over 300 articles, according to Google Scholar, 300 articles, conference proceedings, and books, and has around over 20,000 citations, and was rewarded for his efforts with the Guy Medal for Silver by the Royal Statistical Society. Haavard is going to speak on two applications of the variational form of Bayes' theorem. So please take it away.
Okay, thank you, and welcome. Yeah, this is about two applications of the variation form of Bayes' theorem. It's a little surprising kind of topic, and you can kind of guess what the outline is. It's like, what is the variation form? And then you have the first application, and then you have the second one. Okay, yeah. So a lot of this stuff is kind of ongoing. What we do now in the group is kind of one of the current main things we do for research. Bayes' theorem. Normally you meet it in Stat 101. It's like after second week, maybe you see Bayes' theorem and you think, okay, it's fine. That's it. You know, so this is the first one is it's a clip from The Guardian. It's a belief, bias, and Bayes, and they kind of is not obviously wrong. Okay. The thing is that they make this kind of statement. This is a newspaper. We cannot believe it too much. It's seen as a mathematical formulation of the scientific method. Okay, but not everything in the scientific method is about probability. And kind of is like Bayes' theorem. You think it's about probabilities, but the main application of Bayes' theorem is not about probability. Okay. And this is kind of discussed in length in this kind of book, Probability by James, a Logistic of Science. It's much more a kind of language of, it's like a language for the extension of logic. Okay, and it turned out to be the same thing, and that's why we're using kind of probability, even for a kind of statement that has nothing to do with probability. So in there is a Bayes' theorem, and inside Bayes' theorem, or outside it, there is what's called the variational form of Bayes' theorem. And this is a beautiful result. This is some years old now. There are some kind of predating hints that this might be true, but even before that, quite long ago. But still, this is 88. It's like a 3-page paper where one of the pages are not needed. They do this, and the nice part is a discussion. Okay, there is 3 times more discussion than the paper. And the paper says that optimal information processing and Bayes' theorem. Okay, so what is it? What is Bayes' theorem? Bayes' theorem is kind of the way we kind of process what's coming in. Essentially, we have what they call input information. It's like essentially here is kind of the prior, and this must be the likelihood, and there is some kind of processing rule, and the output is the posterior and the marginal likelihood. So what is? So you can kind of derive theorem, Bayes' theorem for just looking at this from an information processing point of view. How can we process, how can we put all this together so we don't lose any information? It's the same thing that if you go to PDEs, you want to conserve momentum, you want to conserve the mass. You have all this unnatural thing. If you start to lose something, you'll never lose and it goes bad. This is about conservation of information. So how is information defined? Back to the 40s, Shannon and entropy and all this stuff. You can do this, and then you end up that the good rule is that lose as kind of balance is kind of information out, information in, the kind of differential zero. So you kind of want to minimize this one. So what are the rules? What are the terms here? It's a KLD, it's a Kullback-Leibler discrepancy between the kind of the prior and essentially the posterior, if we know what posterior is. Okay. And there is a balance between also the kind of the posterior and the data. So it's expected log likelihood. Okay, there is a minus over our guess for the posterior. And you minimize this kind of expression over all possible classes of posteriors. Okay. And of course, if you do it right, you get zero. Okay. And we know what the solution is. So why should we care about this if we have an equation and we know the solution? Of course, if you plug that in, you get it right. You know? So what's the big deal? The point is that, of course, we don't always know how to compute the solution. Okay, and even if we can write it down in math, we cannot kind of compute it. Of course. So what's the application of these things? And this is sometimes, yeah, this often goes under the phrase variation inference, even though many of the early papers on variation inference didn't know of this result. Okay, so we can kind of just define variation inference as that thing, and you can just define it. But it turns out that this has a good justification. It is the right thing to do. And if you don't know the posterior and you have to guess a class where the solution is in, this is the functional to kind of minimize. So this has the same objective as it's called elbows, like evidence lower bound, variation inference. Yeah, the point is that this kind of, it makes, yeah, it is what I said. It simply makes sense of it all. This is the right thing. And we know by definition that the kind of the solution when you put this in is kind of stable because it's minimize the loss of information. Okay. The point is that traditionally variation inference, if you go to results, this is like a catalog for method that is rough. Okay. You try to get the location right. You have there is no control over the variance, usually. The way it's been defined, very often used, is very, very, very simple, rough, crude approximation that are kind of fast to compute. Okay, so we'll make use of this result in a completely different way to get very precise result. Okay, by doing something else. Okay, to go there, we'll go back and talk about something called Laplace approximations. Okay, that you have heard. This is like things. What is Laplace approximation? It's all about doing approximation of an integral of this type. Okay. Of course, it's an old technique. What do you do if you have to compute this thing and you don't know how to compute it and you have no machines? You know what you do. And then it boils down to what can we compute? If this was second order, we know how to integrate second order. Okay, it's like a Gaussian distribution. So essentially, we do a second order expansion around the mode. Okay, I ignore all details. Okay, around the mode. So the mode is 0, and what you get second derivative, this is a Hessian, and that's it. So this is a normalizing constant of the normal. Okay, this is Laplace approximation. So what can we use it for, and what do we use it for? We use it to kind of compute margins, and this is essentially the problem we have in kind of statistics, is kind of compute margins. We can write down the joint distribution. It's easy, it's there, but I want to know what's happening with one of them. So I have to kind of integrate out all others, and if all others is 1, then I can kind of find the margin of x1, and I just integrate out number 2. It's easy, you know, it's a one-dimensional integration. But of course, here, our aim is to do this dimension 1,000, 10,000, 100,000, a few 100,000. Okay, so we need to kind of work with method that scale. Okay, so how can we do this thing? How can we do this integration? By using this result. Of course, then it's like if x1 is fixed, this is a one-dimensional integral, and we apply this technique for every fixed value of x1. Okay, so this is like a function of x1, where this should be x1. So it's a function of x1. No, it's a evaluated x2. This is a function of x1. Okay, so for every value of x1, we can apply this technique, and then we're using Laplace approximation to do integration. Okay. Second order is simply something Gaussian. So it means implicitly we are approximating another distribution with a Gaussian. Okay. The thing is, we can do these things, and sometimes it's usually fine, but even this is essentially too expensive. But even this one, let's take this one first. What if I do this kind of estimate and I'm not happy? Okay, I think that the accuracy is not enough. I want something better. What can I do? Okay. The obvious thing, this is the very math thing. You just go to higher order. Because we do the second order expansion, I can do more. I can do 4, I can do 6, I can do whatever you like, you know. Yeah, good luck. This doesn't lead you very far, but it's a very math thing. You can do all this math and it leads to essentially nowhere. Okay. Can we use something else than a Gaussian? Yeah, you can approximate any distribution like, as long as you know the normalized component, but none of this will scale. Here, this is dimension 1. We can do what we want. Dimension 100,000, we cannot. You know? So we need to have this kind of back of mind. We need something that can scale to these kind of dimensions. The thing is that how far can we push the Gaussian distribution? Because it's here, but it's very predefined. We match the mode and the curvature at mode. Maybe I can be more clever. And then I can push the Gaussian to go further. Okay. So this is a Laplace approximation, just rewritten. It's a joint divided by the conditional. It's just an easier way, because why? Because I don't like integration. Integration you stopped doing. When you could do exact integration, you stopped. So this is equivalent. It's a joint divided by conditional. When this is approximated by a normal, this is the Laplace approximation. This is the same formula, it's just a rewriting. Conceptually, this is easier for me. Okay, so the Laplace about you fit the Gaussian at the mode. The mode is a mode of x2 as a function of x1. Now we have the variational form of Bayes theorem. The point is that that is also valid conditional. Okay, so when I condition on x1, I have also the same problem again. Okay, so I mean that I can take the Gaussian, and I can apply that, take that Gaussian, and I can put it into the variation form, and I can, in theory, get a better Gaussian. The Gaussian has two parameters, mean and variance. I can correct the mean, probably easy thing, and I can correct the variance. Probably no point to correcting the variance if I don't also correct the mean. So that's the kind of the stage. I can do V Laplace. This is called Laplace method. This is Laplace method. Just doing this kind of Gaussian thing, and I can correct the mean, and I can correct the mean and variance. What I mean by correct the mean and variance, I'm gonna have to spool back. Go back here. Sorry. I put it in here, and I'm solve this optimization problem as a function of x1 to get a better mean or a better mean and variance. Okay, how is this? Yeah, it's not difficult. Think conceptually, it's all fine. So what are the results? Here is just a standard logistic example. Follow up from the last talk. It's also about logistic regression. So what does the problem look like? It looked like this, something quadratic. This is not important. This is something quadratic, and there are something non-quadratic in log scale. So we have this thing. So from this here, I want to kind of integrate out x2 to get the margin of x1. It's very, very simple. So I can do all this kind of thing. And here are some results. These are the, okay. The point is that if everything is nice, everything works. Okay, now here it starts. Okay, this is fine. This is okay. Let's start here. Let's see here. This is what I get if I take the joint Gaussian in 2 dimensions and fit the mode and compute the margin for that one. And this is pretty not very accurate. The blue one is the truth. And this guy here, this strangely thing, is what's called a Laplace approximation. So normally the best thing we can do that maybe scale. Okay. The thing is that instead of matching the Gaussian at the mode and the Hessian, I can do this variation-based correction for this. And then if I do it for the mean and variance, I get here almost fit the line. I think this is even this is extreme. Just to you want just to kind of tune parameter just before it crash. Okay, just to see what happened. And the Laplace approximation is still not too bad, but it has a bit this funny shape. But you see here, if we correct the mean and variance, then we almost get it right. Even this one. You see. So the point is not we can push this. What does it show? Is show that we can push the Gaussian. Or the thing is we can push it much further than we or at least me I thought we could. Okay. So why is it important to push the Gaussian? Because in high dimension, this is essentially the only thing we can compute with. You can say, I heard about another one. yeah, good luck. Normally, it's either the Gaussian or something that is kind of just a function. The mapping of that one is the only one that essentially we have the normalizing constant that we can compute. We have the linear algebra. We have everything that goes with it. Okay. Many other distributions doesn't necessarily have a closed form normalizing constant, and there are some that have that you cannot compute in this kind of dimensions. Well, yeah. Correct. Yeah. Sorry. The point is that this is the one I'm playing with. So for every value of x1, I have to compute a new Gaussian. Yeah, so you don't see the Gaussian. Essentially, you see the mode, you see implicitly the mode as a function of x1 and the Hessian as a function of x1. You don't see the Gaussian, but it's still there. Yes, this one. If I match the mode and the curvature at mode as a function of x1, this is not possible. I can compute it. Yes, in closed form. Yeah, no, semi-closed. I have to solve this minimization problem to get the mean. I can get a better mean, the variance, than the one I can get from the mode and from the Hessian at the mode. Yeah, thanks. Yes, why are we doing this? It was mentioned because we're doing this inline stuff, and this is the page. This is towards like a long-term effort to kind of improve accuracy, reduce the speed. No, to have better speed, more accuracy, better speed. Okay. The point is that this has been going on, as Jay mentioned, for years, and we know what is important and what we know what is less important. And we need to do, there is a lot of ongoing works, and this kind of ideas is a very essential part of it because it allows us to scale things in a completely different way than we could do before. Okay, so what is, sorry, just want to say there is in this inline stuff is working for what's called latent Gaussian models, and essentially it is something Gaussian, and you have some observation. We saw that you had two-dimensional Gaussian and you have binomial observation for the logistic regression. Sometimes there are kind of extra parameters here that I simply have ignored, and this comes in here. The thing is that this is low dimensional, 5, 20, 25, 30. This is high dimensional, 1,000, 10,000, 100,000, 200,000, maybe a million sometimes. This is from 10 to some million. Okay, so this is the scale we're working with. Okay, so to have something working in dimension 10 has no value. Okay, you must scale in some way, otherwise it's someone else can do that. Okay, and from this we have to compute marginals. So it's the same problem, but this is harder, but the idea sounds okay. Let me show you one example how the equations kind of look like, because we just seen them kind of abstract. This is like Poisson count. So essentially, if you simplify things, we need an approximation to this guy here. There is something quadratic in x axis or Gaussian unknown. Okay, and then we have data. These are counts. This is a linear term that just do a shift. It's just a tilting. And then we have a non-quadratic terms. Okay. So we need kind of, so what is needed is kind of approximation to this guy that we also need. We also have a normalizing constant for. Okay. And then we also need kind of marginals to this one. I have to take this guy here and to integrate everything else but one of them. So these are the essentially the thing we need to kind of compute. Okay, and then you kind of see how natural kind of doing things with the Gaussian, because we are already here. This is Gaussian, and this part of the likelihood is also Gaussian, and only this part is non-Gaussian. Okay, so we are almost there. Okay, just need to kind of get it done. Yeah, so the starting point, skipping kind of constants, is that this guy here is approximately, we approximate this around some kind of point to get kind of a quadratic. And then you see that the rough mean and the variance is just the linear solve and the inverse of a matrix. Of course, you can compute the inverse of the matrix because it's high dimension. But the good thing these matrices are, we define them to be sparse, so we construct things so they are sparse, so we can do a sparse inverse, so we can compute the diagonal on this guy. Okay, this one doesn't work well. This was the curve that was really bad. Not the Laplace one, but the other one. So this one is way too rough. But these are kind of this. Since we are in this learning environment, it's often called the Laplace method. And those using it are usually super happy with the results. Okay, but they're not very accurate. Okay. So the thing is, can we do better? And the thing is, if we want things to scale, we want things to scale. So it's not that I want to compute one marginal better. I want to compute all marginals better at the same time. Okay. So if I only concentrate on the mean, then I keep this inverse here is the covariance, or this is the precision. So I want to correct the mean. What can I do? So I rephrase this. This is the kind of the rough estimate. Now we take the variational formulation and we apply it in a completely new way. We use it to correct that one. So if I have a good guess, I just want something better. And I know that the variation form will give me something closer, better, in a stable way that is closer to what I should have. Okay. Yeah. So here is a trick. If we want to correct the mean, we don't correct the mean, we correct the right-hand side. So kind of the contribution from likelihood. And I know exactly where the important contributions are because we are doing this for a long time. And I know exactly we want to mainly correct here, here, and here, and the rest is kind of implicit. This means that essentially we define that we have a low rank correction. We correct using kind of intercept, fixed effects, and a selection of the other ones, and we get them to dimension 100, 200, around that size that we can use to correct a million. Okay. So it means that I have a few of those that are non-zero that I want to kind of optimize over, and the rest are set to zero. But the impact for the mean everywhere is non-zero. Okay, it's beautiful. So I do a joint approximation. It's wonderful. Yeah, there is a question. No, I don't know. I don't know what theta I is, but I know where it should be non-zero. Here. Yeah, we've been doing this for years. We know exactly what to do. Yeah, I can tell you. Yeah, it's not important. You know, I can choose. I choose you, and you can do this. It's not difficult. We just in the beginning you think, oh, everything is important. No, it's not. Something is more important than others. Okay, and that's the thing. So I know where I should put this, and that's fine. Here is just an example. This is my time series. It's like smoothing of counts. You cannot see. There are some differences. I zoom out this area here, and here you see the kind of what's called Laplace method. What you get from the joint Gaussian approximation. Okay, and here is the Laplace approximation, and there's new correction. They are just on top. Beautiful. One is expensive to compute. The other one is cheap. Okay. One scale, the other one doesn't. Okay. Beautiful. Here is another one. It's a space. It's like a survival model. Doesn't matter. Here are some unknowns, and here are these kind of variation by these kind of corrections. They are spot on the kind of the best we can compute. And here is a 1200 seconds. We need, because it doesn't scale. We normally we don't do that, but we can do it. But this was computed with old version. Now we're down to 4 seconds, 4 or 5 seconds. So it's a huge cost reduction. It's more stable. And it scales better. Everything is beautiful. The thing is, what can we do about the variance? We corrected the mean, the variance. The variance is hard. Okay. Why? Because it's defined like this. It's take that matrix and this matrix, and you have to control the inverse. So you have an enormous matrix that you can kind of play with. But you cannot invert it. Okay, you can invert something. And it turns out, yeah, here I tried to do it's a diagonal matrix. It's a product of diagonal. It's element product. I think. So we have the same delta thing. We can apply the same idea. It's beautiful. The point is that practical, scalable? Yeah, kind of the maths say that this is so. We also have to use results from kind of sparse numerical method. What we can compute and what we cannot compute at what kind of cost. And this is still work in progress. I'll just show you some results. Here again, time series model, Poisson counts, same thing. This is a pretty extreme result. Extreme. Just to kind of push it, you kind of push until it almost fall over. Okay. So this is what we get with the same variance that we had before. And this is the new variance. Here variance is overestimated. This doesn't happen often. Once in a while this happens, and this kind of get it right. So it seems like, yeah, we can do that. We have still work to do. It's still work in progress. But the idea that we can do that, and of course, if you can correct mean and variance, you can correct mean, variance, and mean, and then you have both. So it's like a very nice thing. Okay, last part of talk. Second application. Application is not this kind. So this is the same equation. It's the same variation form, and this is a long-term collaboration between this guy. He was here like for the last meeting, the fall 2018. Yeah, he was here for this meeting. He's clever. So what is it? You can start in the other end. I have to go over here. So what is is there an optimal learning algorithm? This is a workshop for learning. Okay. Is there a kind of meta result saying that this is how we should learn? And you think, okay, learning is a little bit like Bayes Theorem. Huh? Oh, just talking Bayes Theorem. No. Okay. Is there a way to do this that is kind of generic? Maybe, yeah. The complement of maybe is also maybe. Maybe there is something. So well, you see all this problem. We have to kind of reject what we don't. The false information we keep, the useful one. You have all this kind of what does do that mean? Point is, if there is a good one, if there is a meta one, maybe it's an unattainable one. Okay. Maybe we can only derive approximations from it. Okay. And then come the kind of the test. Maybe we have it, but we don't know it. We have examples like good algorithm that works. They learn. Learning is kind of optimization. Okay. Regression, Newton method is old one. It's still good for doing optimization. Huh? Still good. Kalman filtering, stochastic. You heard about this kind of gradient descent. You have stochastic descent. You have these new algorithms from learning, RMS prop, dropout. All these are kind of, they work. They are kind of a little bit ad hoc derived. You can derive from some way. Some are kind of, oh, this works. It's a little bit what you heard earlier today. Yeah, you do this hack and it's working and you don't know why. Okay. Is it possible that there is an origin of not species but algorithms? Okay. Go back to Bayes Theorem. Okay, this is about information processing. The point is, yeah, you can. We will not do that. Here we define things as a log likelihood, that we have a likelihood. You can also define this in a more generalized context where this is a loss. Okay, so you can go and generalize Bayesian inference where you don't have a likelihood, but you have a loss function in a way for the data. Okay, yeah, prior you can talk about regularization. Yeah, the base general based. And then you have this kind of class of distribution that you can play with. Okay, it's not about computing things, it's about selecting a class and finding the best one in that class. Okay, exponential families. If you go to exponential family, included conclusion, you can kind of think, we can do better. We can do mixtures. This is obvious thing. You know, you just have, instead of 1, you have 2. Okay, instead of 2, you have 3, and so on. Okay. So how, just to give you, this is just to give you the flavor of the result. How do we minimize a function? You do gradient descent, and you do Newton-Raphson. This is about the Hessian. What is this guy doing? Why is it working so much better? Because it's correct for the local geometry. Okay, it says something about the second order properties that is all about geometry, about distance. Okay, it's essentially how the variance depend on the mean, to put it roughly. Okay, if the variance is constant, then this guy is constant, and essentially this guy is more or less the same. Okay, more or less. So this is a good thing. Okay, if we go to exponential families, there are something funny happening that mimics gradient descent to Newton method. Okay, so this is exponential family. It's a family of those who are exponential. If you have natural parameter, that is here. You have sufficient statistic. You have these functions, but you also have the expected values. Okay, that is like the moment, like the mean, the covariance. Okay, these things, and then you can define something called the natural gradient. The natural gradient is tilde. So okay, so what is this? The natural gradient is a gradient scaled by this, what's called a Fisher information metric. It's essentially the same thing that we go from a gradient descent to a Newton method. You scale by the second order information. Here it's in the expected value, it's in theory, okay? Very useful result is that the natural gradient for natural parameter is the gradient for the expected value parameter. We can kind of compute this implicitly without doing this kind of fuss by simply, instead of using the gradient for lambda, we can use a gradient for the mean parameters. Okay. Then, if we go back again to this kind of Bayes theorem in this variation form, it's the same thing. Then we can kind of learn, this is what we do. We have this natural parameter. We can use a natural gradient. So it's essentially the expected value for the expected values. So there's a gradient for the expected values. That would be the natural gradient for the natural parameters. The point is that by using this one, this say two things. It say what you should minimize, and it's also say or how you should kind of learn from this. Okay. The point is that again, this unattainability is a bit of an issue. You know, we cannot compute the truth, but everything is like a projection of what we would like in theory to what we can do. So we have to then you can play with various approximations, give different algorithms. What is a class of candidate distributions? You have exponentials, families, you can have this type, you can have this type, you can have various kind of approximations, give different algorithms, and also how do you approximate expected values, and how do you approximate gradient? Maybe you use stochastic. Okay, just say something. Okay, here's another approximation of something gradient. Here, I'm just forget about the math. Here the result. You know, if this class here, just a normal with some unknown mean and a fixed covariance, this gives you gradient descent. If you also adapt the covariance, you get the second one, the Newton method. And you can get multimodal optimization if you go to mixtures. The point is that higher complexity in the distribution that we propose, by some kind of magical interaction between the natural gradient and like the entropy term, magic happens and things just get more complex. You can do better. So here, you naturally go from gradient to Newton method simply by estimating also this one, even though the algorithm using gradient method. You see? Beautiful. And it's all just come together. In the paper, there is a long list of algorithms that you can derive. You can derive from, let's do this and choose, and then we get some of these. You see this dropout, this RMS, this kind of AI deep learning algorithm. They come directly out of this. Conjugate Bayes Laplace method, EM algorithm also follows stochastic EM. All this long list of this one is also all discussed in this conference. So what does this show? Yeah, this is the interesting thing. Maybe this is our kind of learning, the optimal learning algorithm. Okay. Just to sum up, the variational form, this is a game changer, at least for me. It's like variational inference. Read the literature, it's totally different. We can apply it to get high accuracy corrections by doing it differently, by simply applying this kind of variation form. Okay. And this is also very, it's beyond, yeah, I don't understand why, but that we're able to kind of push Gaussians so far, we can change it. We can, instead of Laplace matching the mode and the Hessian, we can compute where to match and how to correct the local Hessian so that it gets it. It is amazing. Yeah, at least for me, I never thought we were able to do this. And then we are also rewriting this kind of package all in this. There's a huge, enormous way of job. So we gain both speed and accuracy in some way. We cannot do skewness. Skewness is a mystery because there is no equation that say anything about skewness. It's all about, as soon as you're Gaussian, it stops at second order, What about skewness? It's not there. There is no equation for skewness. So this is a bit, it's a bit of a mystery. We haven't solved that yet. The other thing is learning out. This is highly, highly surprising. Okay, my view. This this the origin of algorithms? Okay. I don't know. It's at least the best. I think it's the best guess we have so far. And if someone else come along and prove me wrong, I'm fine. But I think it's pretty amazing that all these kind of algorithms that turn out to just works, they have kind of stood the test of time. Okay, and you can derive them from scratch. You don't need to invent things. You can derive them. You can make simple choices in general assumption. You can do the math. Oops, and it appears. Yeah. It's amazing. Okay. So maybe no more ad hocery. Maybe no more this works, but nobody knows why. That's a little bit what we heard about today. But of course, Bayes' rule, he didn't know about the cost of parallel programming. He probably knew about the cost of communication. He probably knew that. So if he wanted to do something, maybe he wanted to be alone. He knew about that, but not in this kind of computational framework. Okay, so that's it. Thank you so much.
Thank you, Haavard, for your talk. Do we have any questions for Haavard? Yep. But do you...
Yeah. Okay.
Hello, thank you for a very good presentation. Actually, I follow up your work, for this Bayesian rule. Yeah, because like I have a discussion before with MT about this.
Yes.
This is very good work because like when we look at it, it's actually from my point of view. Like in the sense of this one, it's actually more like to me, it's like Langevin diffusion. When we look at Langevin diffusion, we have a steepest descent plus noise. But in this case, is without noise. Yes, my question is that, for example, when we consider the Fisher information matrix, the natural gradients, and we try to fix how to say the mean and the covariance when we do the step at each of the learning algorithm. Like, for example, it's totally depending on the loss landscape we have. But if the Fisher information matrix is not being approximated accurately, then also the whole approximation will be collapsed, right?
Yeah,
so what do you think of
this thing, yeah, you have a point. Let me wind back here. What is often the case is that very often we don't need to compute this guy because we need this one, we need this guy here, but this is the same as the gradient with respect to the expected values, which is essentially what is natural to compute. So often, like if you go back to the common recursions, there are recursions in exactly the moments. Yeah? You're using that one implicitly. It's doing the kind of the natural gradient in the natural parameters. Yeah, so you have fun. Of course, if you need something and you cannot compute it, you have a problem. Yes. But at least it say what you should aim at. You know? This is the thing. It's like maybe this is unattainable, except in kind of simple cases like pure Gaussian, with Gaussian data and all this kind of learning. This we know. That beyond that, maybe we can never really compute it, but at least you know the reference. You know what you should approximate and what you should aim to approximate. But yeah, you have a point. Yeah.
Raoul wants to ask a question. I'll give you this one. Be faster.
Thank you very much. So two questions. One, in the formulation of the variational, right, that you have this divergence term. All these things, when you do the optimization, are kept within a Gaussian framework, so you can actually compute this DKL in closed form, and you don't need to resort to any sampling or things like that?
Yeah, we can. Okay, so so the variation form, we can, yeah, to compute the corrected mean, we do again a kind of a Newton algorithm. We kind of compute. You need integral with respect to Gaussians, which is conjecture, and you need the KL between two Gaussians that we know.
Yeah.
Yeah. So we do a kind of a second order optimization or the Newton method to get the correction for the mean, and we can do the same for the correction in the variance.
So you
But
keep
we
everything
need
as
to kind of compute this. Yeah, you see,
you
there is,
keep everything
there
algebraic.
is like
essentially.
an iterative algorithm inside here. Yes.
No need to hire or quadrature or anything like that. Just algebraic computations because
Yeah,
you
because,
stay within the Gaussians
Yeah. So why
and
is
everything
this?
is closed form.
Sorry.
That's forward.
Usually because the likelihood is clean. You don't. We have pointwise like. Sorry. We have a pointwise. So the likelihood here only depends. This is like a generalized linear framework, regression. The likelihood of that data depend on that linear predictor. And this is what. So you don't have this. All the data are jointly. You don't have. So you don't have the case that this will require. So condition on X, if you want to do the expectation of the log likelihood, this is just a sum over univariate. Yeah. So this is a construction. This is by construction. This is well behaved. Yeah. Of course, you can think of cases where all the data are observed jointly, like you observe if you have time series model, you observe the time series exact. That is a harder problem. As soon as you have state select model, you have a latent model and then observation. This is easier. Yes. So the log likelihood is just a sum. Yeah.
Okay.
So it's a sum of univariate integrals. Yeah.
The other question that I have is like, can you extend things to actually keep Gaussians as seeds when you actually use transformations of Gaussians, and maybe there's some kind of approximation that you can do?
Yes.
To still have Gaussians at the bottom, but
yeah. So anything that could be derived from Gaussian diet, like pointwise transformation, something like this is within reach. It's still Gaussian in the core.
Yeah.
Like the couple is still Gaussian.
Mm-hmm.
Yeah. But anything there is also a kind of class of distribution where we know and we can kind of play with that one. But we don't have a good application for this. So for a moment, we are sticking to the Gaussian. But still, yeah, you're totally right. This kind of pointwise transformation is all within reach. Yeah.
Thank you.
Do we have any more questions for Haavard? No, if not, let's thank the speaker again. Thank you very much, Haavard.
Okay.
So that concludes the afternoon session. So then we reconvene at 5 o'clock for the reception with the introduction by Omar Canillo in building 19. Is that correct? Thanks very much. Thank you.